Okay, I'm going to get started. Firstly, welcome to 213, second semester of General Physics. I should introduce myself. My name's Tim Gorringe. So I'm going to be the lecturer for the class. You met your recitation instructors yesterday. You'll meet your lab instructors this week. My office is in this building. It's on the third floor. It's room 309. It's close to it's above the bagel shop, basically. Here's the best way of contacting me is by email, this email address here. And here's my office hours. I've got office hours on Monday and Thursday. But if those don't work for you, you can always send me an email or make an appointment. I'm there most of the time too, so you could also drop by. Any questions on that before I go on? Okay. So I wanted to say a few words about the administration of the course and the organization of the course. So we'll do that. I think I've got 4 slides on that. Then I'll say a few words about the overall content, the sort of physics content of the course. I think I've only got 1 or 2 slides on that. And then we'll get on to the first topic that we're going to cover in today's class, and that's charge, electrical charge. So that's the plan for today. This is a list of the things that you're going to need for the class. You're going to have for the class. So you have to have, obviously, you have to have access to our Canvas course. On there is where we'll have the lecture notes. Lecture videos. It's on there where we have the assignments for homeworks, etc. It's on there where you can find and monitor your grades. So you'll need access to that. You'll also need access to the course textbook. It's College Physics by Sir William Whewell, and you'll need access to the related WebAssign homework. So you can get both of these online. You can get them through the first day program, and that's a tab on the Canvas course, and I think that's going to cost you $54 to get electronic access to both of these. If you wanted a hard copy of the textbook, a new hard copy of the textbook's very expensive, but you could get a second-hand hard copy of the textbook. It wouldn't need to be edition 11 necessarily. It could be edition 10, it could be edition 9. They basically have the same content in. The only thing to watch for if you've got an older edition is the problem numbering is different. But anyway, the problem numbering isn't that important because the homework that you'll be doing is the WebAssign homework, and you'll just access that through WebAssign. So those are the things you need. Any questions on things you need or things I need? Okay, if you have any issues with getting access to these things, then you can just send me an email, and I'm sure we can fix it. Okay, got 3 slides. And they're at sort of different magnifications of what we're going to do during the semester. So one is kind of what's going on weekly. That's this slide. Next slide is kind of the semester is going to be divided into three bundles or 3 modules, and so I'll say a little bit about that. And then finally I'll say, for the whole semester, how's your grade going to be calculated? So 3 different sort of magnifications of what's going on during the semester. The way the course will work is kind of a weekly schedule, and that's what's shown on this slide. So in the weekly schedule, each Tuesday, today's a Tuesday, we'll have a lecture class. We'll introduce some physics material. On the Thursday, so this coming Thursday, we'll introduce some material, some new material. On Monday, you'll have a recitation class with a recitation worksheet that covers that material. On Monday night, you'll submit the homework, the WebAssign homework that's based on that material. And so lecture Tuesday, lecture Thursday, introducing new material, recitation class on that new material, homework based on that new material. Is the cycle that we're going to go round and round for the whole semester. This week's a little bit different because obviously you had recitation yesterday, but you didn't have any new material. So it was a review, but that's kind of unusual. Next week's also a little bit different because next week, Monday, is Martin Luther King Day, so you don't get a recitation worksheet on the material. There is homework assigned for this week, which is due on the Monday, but that homework's not for credit. Just like the recitation worksheets yesterday were not for credit, also like the quizzes that I'll give today and on Thursday, they won't be for credit. But after that, after Martin Luther King Day, all these things, the worksheets, the homeworks, the quizzes, they all start counting for credit. Okay, I said the course was divided into 3 modules or 3 bundles that are bookended at the end by a test. So there'd be module number 1, test 1, module number 2, test 2, module number 3, test 3, and that's the way the semester's going to work. The modules cover 3 different themes. I wrote it down here. So the first bundle or module is going to be on electricity. The second bundle or module is going to be on magnetism, and the third one is on space and time and light and matter, which are all related things. So those are the 3 modules or the 3 main topics that we're going to cover. On this slide, I cut and paste this from the syllabus. So this is part of a table in the syllabus that tells you lecture by lecture what material you'll be discussing. These are the lectures that lead up to test number 1. So this is the first bundle of material. This is the first module of material. It's where in today's class we cover electric charge. And then in Thursday's class we cover electric forces. And then in the next week's classes we cover electric fields and electric flux and so on. So it's all listed here. You can find the sections of the textbook here. I've marked over here in red and in blue that the recitation worksheets. So the next recitation worksheet will actually be Monday, January the 20th. No, that's Martin Luther King Day. It will be the following week. It'll be Monday, January the 27th. So that would be the first recitation worksheet. And that'll be the first homework that'll be collected for credit too. And then thereafter we continue this cycle. Okay, so this is now taking even different, a different zoom back for, this is the whole course. How's my grade going to be calculated for the whole course? So this is listed and discussed in the syllabus, but this is summarized in this slide. These are the ingredients that go into your final grade. So tests, lecture quizzes, we do in lecture here, WebAssign homework that you're going to do online, due on Mondays, recitation worksheets that you do in groups in recitation class on Mondays, and the lab assignments. I won't talk much about that. So the 3 tests in total count just over 50% of the class. So each one of them is counting 17.5% of the class. So over half of your grade, just over half your grade is based on those 3 tests. So they're obviously important. Those tests will have fully worked out problems, and they'll have concept questions on that. And I'll say much more about that as we get closer to a test. The other material, the other topics here, the quizzes in lecture, the homework assignments in WebAssign, the worksheets in recitation, they're meant to help prepare you for the test as well as being sort of class credit. So for example, in the quizzes in lecture, we're going to focus on concepts, ideas of physics material, and those questions, that type of question will come up on the test, it's part of the test. In the WebAssign homework and the recitation worksheets, we'll concentrate on solving numerical problems. and fully working out numerical problems. In particular, the worksheets will be graded based on how you describe, how you explain how you worked out a problem, showing all your working out, all your equations, and so on and so forth. So all those things, the quizzes, the worksheets, the homework, are aimed at preparing you for those 3 tests. And then in addition to this material, there's the lab assignments, and as I say, you'll get a discussion of how the lab assignments work and how they contribute to your grade in the lab classes. The grading is done on a fixed 15-point scale. So that means if you get 85% or above, that's an A in the class. If you get 70% or above, that's a B in the class. And if you get 55% or above, that would be a C in the class. So that's the grading scale. Any questions on all that? That's all the administration I plan to talk about, I think. Yeah. It's either really clear, it's really unclear, and there's no question that you can dream up. Okay. I wanted to just give a short course overview, so you get an idea of what we're going to cover throughout the semester before we move on to the course content for this class, which is electric charge. So let's just do that. So this semester, this class, this semester, is about electromagnetism. So electromagnetism is a sort of big fancy word that combines electricity and magnetism and all the results of combining electricity and magnetism. So it's a class really about electromagnetism. If you imagine a really long line from the smallest scales that we know about, size scales that we know about, to the largest size scales that we know about. At the smallest size scales that we know about, what is there? What structures are there? Well, what structures are there are atomic nuclei, and they're absolutely tiny, 10 to the minus 15 meters. At the largest scales, what's up at the largest scales? Well, what's up at the largest scales in the universe is like solar systems, planets, it's stars, it's galaxies. Those are the largest scales. Galaxies are the scales of 10 to the 20 meters, so that's enormous distances. But actually, while nuclear forces govern the world of the tiniest objects, the nuclei, and gravitational forces govern the world of planets and stars and galaxies, in between those bookends of the very, very tiny and the very, very large, the king or queen of that world is electricity and magnetism, is electromagnetism. So you and I are basically electromagnetic. Everything around us, understanding everything around us, the chairs that you're sitting on, the tables in front of you, the room, it's all electromagnetic in its structure. And so this class in one semester, we're going to cover really all of the structure of our everyday world by covering electricity and magnetism. So that's the scope of it. Not to be overly ambitious, just a little bit more detail. So electricity, well, what is electricity? One thing about electricity, one thing that makes it interesting is that it's really the force or the glue that holds together atoms to make the periodic table. It holds together molecules. For example, I don't know anything about this sort of stuff, but proteins and carbohydrates and fats, you know all about this sort of stuff. Holds together those things. You know, we, say our hearts and brains are electrical devices. Our thoughts, our emotions in our little neural networks or whatever there are, those are electrical in origin. And so electricity is very interesting because we're built out of it. Everything around us is built out of it. And there's all these interesting phenomena that emerge from it, from the periodic table to all the molecules to the neurons and whatever. So that's why we're interested in electricity. Magnetism, why we might be interested in magnetism? Well, you might know that the Earth is actually a magnet. The Earth is actually an extremely strong magnet. That's lucky for us, because the fact that the Earth's a magnet actually has saved our lives. The Earth's magnetism shields out harmful, deadly, dangerous cosmic radiation that would otherwise kill us. Without the Earth being a magnet, there'd just be beetles and cockroaches on Earth. That'd be basically it. Anything that could survive large amounts of radiation. So the Earth being a magnet has saved us. Also, magnetism gives us basically our everyday modern lifestyles, our everyday modern technology. This is from like electric generators. That's obviously important. Otherwise, we wouldn't have the displays. We wouldn't have the lights in the room. Obviously, electrical motors. That's a very important thing in our everyday lives. But all sorts of other things, from computers and laptops and phones and so forth, are all involve magnetism. So that's why magnetism is important. What about light? It's another topic of the class. Turns out, I mean, you may or may not know this, that electricity, the force of electricity, and magnetism, the force of magnetism, they can be joined together in electromagnetism. This combined theory of electricity and magnetism. And it has this fantastic prediction. It predicts a thing that we call light. So light is actually a prediction of electricity and magnetism, and it's a bundle. We think of it as and we'll see this, we think of it as a bundle of electricity and magnetism. And of course, light is important, right? Without the sun and its light, without sunlight, again, we wouldn't be alive. So without electricity and magnetism and electromagnetism and its prediction of light, we just wouldn't be alive. We use the energy from the sun that's arriving from the sun in the form of sunlight. It supports our life. Finally, a topic that we'll cover is space, time, and matter. So right towards the end of the course, we're going to take our understanding of electricity, magnetism, and light, and we're going to kind of focus it on the microscopic structure of matter, atoms and molecules. And we're going to understand the microscopic structure of atoms and molecules with our understanding of electromagnetism. We're also going to take our understanding of electricity and magnetism. This is even more interesting, really. And we're going to focus it on space and time in which we live in. And we'll discover a new understanding of space and time by focusing our understanding of electricity and magnetism on space and time. We'll discover things like space and time are stretchable. And we don't think of them as stretchable, but we'll discover that's the true nature of the space-time fabric. So these are all the things we're going to talk about. Any questions on all that? Okay. So now I can actually start the class. And today's class is really just on sort of one topic. It's the topic of electric charge. And in discussing the topic of electric charge, I want to go through these few bullets here. So this is what we're going to cover. I'm going to talk about, before I talk about electrical charge, I'm going to talk a little bit about the discovery of electrical attraction and electrical repulsion. A little bit of background history. We're then going to talk about how we can explain that electrical attraction and electrical repulsion in terms of electrical charges, actually positive and negative electrical charges. So we'll explain the attraction and repulsion. In doing that, we're going to realize, I mean, we might have realized it already, that matter, materials, are made of electrical building blocks. And we're going to talk about some basic properties of matter, insulators and conductors, because they're made of electrical building blocks. So that's this bullet here. And then right towards the end, I'm going to show you a couple of devices. One's here, and one's over there. They're called a Van de Graaff generator, they're called an electroscope, and we're going to use those devices in this class to basically harvest electrical charge and measure electrical charge. So these are instruments of working with electrical charge. So that's the plan. Okay, so I said I'm going to start with, this is always really popular when I start talking about history. We're going to start with a history lesson on electrical attraction and electrical repulsion. But it's going to be short. So it's one slide and a demonstration. The first record of electricity, electrical attraction, goes back, of course it goes back to ancient Greeks. So it goes back like 2,500 years. And so those are the first records of electrical attraction. And it was specifically that a material called amber, which is from tree resin, right? And it's used in jewelry. If you rub that material with your shirt or whatever, it will then attract small objects, like it'll attract your hair, or if you sleep on a straw bed, right? It'll attract the straw or the straw bed. So it will attract light objects. And that was what was recorded by the ancient Greeks as what we think of as the first record of electrical attraction. Of course, this is me thinking now, it's not that the Greeks, surely it's not that the Greeks were the first to discover this. They were the first to actually write it down. Presumably Neanderthals, which we now know are very intelligent, they had discovered it, but they never wrote it down. So this is the beginning of the records of electricity and electrical attraction. A breakthrough was made, this is 2,000 years later. So nothing happened for 2,000 years in electricity, and then 2,000 years later, an important discovery was made, which was that it's not just that amber is some special material that can attract hay or hair or whatever. Actually, just about any material, if you rub it enough, can attract other materials. So amber wasn't special. All materials can exhibit electrical attraction, and so that was a big breakthrough, and that was due to this guy William Gilbert. The next breakthrough I've listed on here, which was just only sort of 100 years later, this is a really important one, is that there's not just electrical attraction between objects, but there's electrical repulsion between objects. So this was a massive change, a huge change in thinking about electricity. Now, gravity is always attractive, but suddenly it was realized, or suddenly it was observed, that electricity can both attract and repel. Big breakthrough. And it was discovered that there are basically two types of materials. You could classify materials as two types of materials. I'm going to call them glass-like materials and plastic-like materials, because glass and plastic are examples of these two categories of materials. And like materials, so two glass-like materials, or two plastic-like materials, if you rub them, they repel each other. If you rub a glass material and a plastic material, those two will attract each other. So they discovered that there's attraction and repulsion. They discovered that there's two classes of materials, glass-like, plastic-like, and they discovered that if you've got like materials, two glass-like materials, they're repel, two plastic-like materials, they're repel. If you've got unlike materials, a plastic and a glass-like material, they're attract when rubbed. So that was a huge breakthrough, and that's this bullet here. I want to demonstrate that. This one's a little bit hard to see if I demonstrate it at the front of the room. So often I will do real demonstrations. This one I made a few videos of. So we're just going to watch the videos of me demonstrating it, if I'm capable of doing that. Okay. Maybe I turn the lights down a bit. Kind of set the mood for a video. So this first video is to show you, you're going to see in this first video 2 glass rods and 2 plastic rods. And I'm going to show you actually that if you don't rub the glass rods, or don't rub the plastic rods, there is no attractions or repulsions between the glass rods. So I wanted to show you this because I'm going to make a point about it at the end. Here's a glass rod. I put it on this little turntable. It's a very nice turntable. If a force is exerted on that glass rod, it will spin around on that turntable. So we can see forces either. Got another glass rod. So these are 2 glass-like materials, and they exhibit no attraction or repulsion. And that's because I didn't rub them. Sounds kind of obvious that they're not going to attract and repel each other, but I'm going to talk about that in a moment. Now I'm going to show you the sort of plastic rods that I use. This is a black plastic rod. Again, I'm going to put it on the turntable. It's very free to rotate on the turntable, so if it experiences a force, it's going to rotate clockwise or counterclockwise. I'm going to bring up another plastic rod, not rubbing either of these plastic rods. No force between them. There's no movement. So 2 unrubbed plastic rods don't exert forces also, and then there's a final combination, and this is a glass rod and a plastic rod. So this is unlike materials, which if you rub them, we've said would attract, but if you don't rub them, what's going to happen? Nothing's going to happen. Now that sounds like,
ever since Kimora was a little girl, she had her sights set on the sky.
That sounds like a rather dull and uninteresting fact. But as we expose the electrical nature of matter, we realize that it's actually an amazing fact, because inside the glass rods and inside the plastic rods are huge, absolutely huge amounts of charge. If that charge was exposed, there would be absolutely huge forces between the glass rods and the plastic rods. And it's only because inside a glass rod there's a perfect balance of positive and negative charges. Inside the plastic rod, perfect balance of positive and negative charges, that we see no forces. There are actually huge forces between those glass rods, those plastic rods, and the glass and plastic rod, but they're all cancelling each other out because there's equal amounts of positive and negative charges in the glass rods and the plastic rods. So it's an interesting fact when you understand the electrical nature of matter. Okay. This one...
And Spectrum Internet brought the sky to her fingertips.
I don't know why Spectrum has to get in here, but that's... this video, let me stop it. I'm going to show you attraction and repulsion between glass rods, plastic rods, and glass and plastic rod combinations when I do rub the rods. So now I'm rubbing the rods, and what that's going to do is basically expose the electrical forces, the attractions and repulsion between the rods. So let's watch this one. This is a plastic rod. Here I am rubbing it. Put it on the turntable. I've got another glass rod. Put that up to that one, and look, it's running away. It's running away because there's a repulsion between those two rods. And so that's electrical repulsion between two like materials. Going to do the same thing with the plastic rods now. So here's one plastic rod. I've rubbed it. I'm going to get another one. Rub that. This is cat's fur. And we're going to see that there's repulsion there. The rod on the turntable ran away from the rod in my hand. And then finally, so those two cases were electrical repulsions between light objects, two glass objects, two plastic objects. Now I'm going to do glass and plastic. So I've rubbed the plastic object rod and put it on the turntable. Now I'm rubbing the glass object rod, and I'm going to bring it up. And this time, we see it's attracting. The glass rod is attracting the plastic rod. So unlike materials, glass and plastic attract one another. Okay. So that summarizes those little videos, basically summarize 2,500 years of work on electricity. What I'm now going to turn to is the modern explanation of what's going on with that attraction of repulsion of glass-like and plastic-like objects. What's at the heart of that? Why is there that attraction and repulsion? So the key is, and I've sort of alluded to it, and you already know it, but charge, electric charge, is the origin, the source of that attraction and repulsion. So we're going to talk about that. Okay, here's the explanation. And my explanation here is a kind of a list of bullets. It's a list of bullets about what is the nature of matter, what is the effects of rubbing on the glass rod or the plastic rod, and thereby what's the origin of the attraction or the repulsion between the glass and plastic rods. So what's the nature of matter? Well, we were using a glass rod and a plastic rod, and I didn't talk about it much, but I was rubbing the glass rod and the plastic rod with two types of material. One was fur, cat's fur that I happened to have, and one was silk that I also happened to have. All of those materials, the glass, the plastic, the cat's fur, the fine silk, they're all made of atoms and molecules. And those atoms and molecules are made of atoms. No, those molecules are made of atoms. And those atoms are made of charged building blocks. So they're made of electrons, negatively charged. They're made of protons, positively charged. And electrons and protons are basically the most basic packets of electrical charge that we know of. So a proton is a little packet of positive charge, 1.6 times 10 to the minus 19 coulombs. Coulombs is a unit of charge. So it's a tiny, tiny, tiny packet of charge. And that's the way I think of protons, just as little, not packets of salt and packets of pepper, but packets of positive charge. Electrons are tiny packets of negative charge. They're tiny packets of minus 1.6 times 10 to the minus 19 coulombs, the unit of charge. They're those little packets of charge. And again, I think of electrons as like little building blocks of negative charge. So the atoms are made out of negatively charged, positively charged building blocks that we name electrons and protons. What's the effect of rubbing? What's all this rubbing going on in these experiments? Well, when you rub the glass rod with the cat's fur, say, or you rub the plastic rod with the silk, what you're doing in rubbing, remember, is that the glass, the plastic, the silk, the cat's fur are materials that contain huge numbers of electrons and protons. So they have these electrical building blocks. What you're doing when you're rubbing is rubbing electrons off one material onto the other material. So I can honestly never remember which way round this is, but let me just, invent it. If I rub the glass with cat's fur, then the electrons are rubbed off the glass, or some electrons are rubbed off the glass onto the cat's fur. So electrons are transferred off the glass onto the cat's fur, and because of that, the originally electrically neutral glass and electrically neutral cat's fur become electrically charged. The electrically neutral glass has lost some electrons, so it becomes positively charged. The electrically neutral, originally, cat's fur has gained some electrons, so it's become negatively charged. So they get charged by the rubbing. And the same if you rub the plastic rod with the silk. What you're doing by that rubbing is scraping off, is transferring electrons from one material to the other material. And again, I can't remember which way round it is for the plastic or the silk or the glass and the cat's fur, but you transfer electrons from one thing to the other thing, making one positive and one negative. So that's what's going on here. The reason for attraction and repulsion, then, is if you have two positively charged objects, two like-charged objects, that repels. If you have two negatively charged objects, again, that's two like objects, that also repels. And if you have two oppositely charged objects, a positively charged and a negatively charged object, that attracts. So we've replaced the idea of glass-like objects repelling one another, plastic-like objects repelling one another, but a glass-like and a plastic-like object attracting one another with a pair of positive objects, like charges, repelling, a pair of negative objects, like charging, repelling, and a pair of opposite charges, a plus and a minus, or a minus and a plus, they're going to attract one another. So that's the explanation. So this is a modern day explanation. We've only known about electrons and protons for not much longer than 100 years, and so it's bringing us comparatively up to date. This is just a graphic of what's going on. In the slide here, here's a rubbed plastic or rubber rod, and rubbing the plastic transfers electrons onto the plastic or the rubber, so it became negative. Here's a glass rod. Rubbing the glass with the cat's fur transferred electrons off the glass onto the cat's fur. It became positive. So the glass has a deficit of electrons. It's lost some. The plastic has a excess of electrons. It's gained some. So this is opposite charges. These attract one another. On the other hand, if you had two rubber rods that you've rubbed with, say, silk, you've made them both negative. They've both got excesses of electrons, and so they're like charges, and they're going to repel one another. And the same would be true for two glass rods. They'd both be positive. They're like charges. They're going to repel one another. And so that's a graphic of our modern understanding of what's going on. Oh, I got a quiz. So this is practice quiz. Practice for you. It's practice for me. It's probably bigger practice for me. So I'm going to publish the quiz, and I'm going to give you just a couple of minutes, because this is a quiz that's not for credit, to answer it But this is practice for next week when these quizzes will count for credit. So the time now is 10:10. I'll give you, say, to 10:13. It is January the 14th, is it? Yeah. And so I'm going to publish this, save and publish. And I'm going to give you these few minutes to relax, unwind, think about the quiz, answer the quiz. You can talk to one another and discuss it. I mean, no fights or anything like that, but feel free to discuss it and come up with a group solution on this. I'm going to put the question back up here. The question is, a glass rod is rubbed with a silk cloth. After rubbing, do those two objects attract or repel, basically? Okay, I'll get started again. If you had any problems with that, you can send me an email. But as I say, this one was just for practice. It's not for credit. When you rub the glass rod with the silk cloth, which in my little videos, I never did that combination. But whatever you do when you rub something with something else is you're going to transfer electrons from one to the other. Now, I don't know which way it's going to go, but one is going to become positively charged, one of the objects, and one's going to become negatively charged, because one's going to lose some electrons and one's going to gain some electrons. One's going to have an excess of electrons and one's going to have a deficit of electrons. So they're going to be oppositely charged. So they're going to be attracting one another. So the glass rod and the silk will attract one another because they have opposite charges. So they attract one another due to their opposite charges is the first answer on the screen here. Everybody okay with that? Good. Oh, here's an interesting question. Just going back to the Greeks. They rubbed amber and it attracted hair or fur or straw. But they didn't rub the hair or the straw or the fur. They just rubbed the amber. So they found that a charged object, the amber, actually attracts a neutral object. That's the hair or the fur or the straw. So that's actually very interesting and not a case that I discussed with the glass rod, the plastic rod, the cat's fur, and the fine silk. So what's going on there? what's going on there is quite an interesting thing, and it actually contains some real big clues to the nature of matter and the nature of the electrical force. And so this slide is a depiction of what's going on here. Here's the amber, and I've rubbed the purple amber, and it likes electrons. It has an affinity for electrons, so it's become negatively charged. That's what all these minus signs are. Here's the rectangular piece of straw or hair or whatever that's being attracted. The red arrows are the electrical attractions between these two objects. Why is it being attracted? The reason it's being attracted is that it itself, that little piece of hair or that little piece of hay or that little piece of fur, is made of charged building blocks, electrons and protons, like everything else is made of charged protons and building blocks. The opposite charges get attracted towards the amber. The like charges get repelled from the amber. That's our rules about attraction and repulsion between positive and negative charges. So you see that in my picture here. Inside the atoms or the molecules of the straw or the hair or the fur, the positive ends are being attracted to the amber, negative amber, and the negative ends are being repelled by the amber. So the positive ends are closer, the negative ends are further away. The attraction occurs of a charged object with a neutral object because the opposite charges in the neutral object get pulled closer and there's a stronger attraction. The like charges in the fur, they've been pushed further away. They're further away and there's a weaker attraction. And so the stronger attraction of the unlike charges wins over the weaker attraction of the opposite charges, and you get a net electrical attraction by a charged object on neutral objects. So that's how it works. It's really interesting, I think, because it reveals that that neutral object, that hair or that hay or that fur, that must be made of charged building blocks for this to happen. It must be an assembly of charged building blocks that get rearranged by the presence of the charged amber. So that's one thing you learn from this Greek experiment. They didn't learn it, but we now know it, that it's a clue to the fact that the hay, the straw, the hair, the fur, they're made of charged building blocks. And another important thing that it reveals is this only works if it's true, right, that if the charges are closer, the forces are stronger. The attractive force is stronger, and if the like charges are further away, then that force, that repulsive force is weaker. So it's actually telling us something very important, that is the entire content of the next class, that the electric force gets weaker as the distance between the charge gets larger. The electrical force between the positive charges and the negative charges is larger because they're closer. The electrical force between the negative charges in the amber and the negative charges in the straw is weaker because they're further away. It's telling us that the size of the force depends on the distance and shrinks as the distance grows. So fantastic stuff. Let me do a real demonstration, perhaps. I just finished this before the class because coffee wasn't even enough. I had to have a Diet Coke. Here's the can. It's electrically neutral. We now know, of course, that it's filled with electrons and protons that are building blocks of nature, but overall it's electrically neutral. If I bring up this piece of plastic pipe, nothing. Absolutely nothing. I'm going to bring up the piece of plastic pipe after rubbing the plastic pipe, but the first thing I'm going to do is put on the camera. If I can. So just to orientate, here I am. Here's the Coke can. Orientate me. And here's the cat's fur. And so what did I say I was going to do? I said I was going to, there's no attraction or repulsion here. I said I'm going to rub like rubbing the amber, I'm going to rub the plastic pipe. The plastic pipe's going to get charged up. The fur's also going to get charged up. They'll be oppositely charged. But then I'm going to bring the pipe up close to the Coke can. Now I've got a charged object and a neutral object, like the amber and the hay or the fur or the whatever, and we'll see what happens. And that's electrical attraction of a charged object with a neutral object. And that is proving, right? That's an easy experiment. You can go home tonight and do it in your kitchen. It's an easy experiment, but it proves that matter is made up of electrical building blocks, and it proves that the electrical force gets weaker with distance. Okay. Okay, so let's go back to the overheads. I want to summarize some stuff. There's a few people that I'm fans of. Martha Stewart is one. I like cooking shows. We'll meet others later on. But I asked her for some comments on the importance of electrical charge. So let me just go through the comments. And let me use the pointer, which I've lost. Okay, over here. So this first point that she makes is that space, time, mass, and charge are the building blocks, kind of the dimensions of nature, from which everything is made. Now, space, time, and mass, you met in 211. Those were the dimensions of 211. All we're going to do in this class, if I want to trivialize it, is we're just going to add one more dimension, and it's called charge. So the entire semester is going to be about supplementing the space, time, and mass, the dimensions of 211, with one more dimension, the dimension of charge. So these are the basic building blocks of everything around us. Not surprisingly, she says an analogy to this is that if you do home baking or whatever, then the flour, sugar, eggs, salt, those are the basic building blocks, just a few building blocks out of which you can make all these different types of cakes and baked goods and things like that. So that's her analogy. I asked her to stop with the analogies at that point, and so for the second and third bullets, we don't have her analogies. That charge is a basic dimension of nature. The most basic things that we know about it from observations are that that charge comes in little packets. They're always the same size. The negative packets are electrons, what we call electrons, and the positive packets are what we call protons. So everything around us is made up of these little equal-sized, opposite-sign packets of charge that we decided to name electrons and protons. So that's an important point. There's an important point, another important point about charge is that you can't destroy that charge. You can't create new charge. You can't just make some new charge in the back garden or whatever, or destroy some charge. Charge is conserves. So that's an important characteristic of those packets of charge. They're indestructible and unmakeable. Third bullet. As I say, this charge that we've been discussing in this class, that's the entire topic of this class, is the root of all our everyday, it's the root of our lives, and it's the root of our everyday world. So out of this charge, this simple idea, you've got positive and negative charges, they exhibit attraction and repulsion. Out of that comes let me list some, we would say, emergent phenomena, right? The periodic table, this whole spectrum of different types of atoms, more than 100 atoms, that comes out of these building blocks. That's sort of amazing. And you think about the periodic table, there's all sorts of materials with different wonderful properties. So that's kind of remarkable. Out of those objects, which are made of charges, right, comes molecules, right? And the molecules, things like that we're built of, like carbohydrates and fats and proteins and so forth. That's all electrical. And out of those molecules that are electrical, that are built out of electrical atoms, that are built out of the electrons and protons, comes things like other electrical objects like neurons and networks of neurons that ultimately are, our thoughts and emotions. So we're all built out of, we're all emergent phenomena from the fact that there's a dimension of nature called charge that has positive charges and negative charges that attract if they're opposite, and that repel if they're like charges. All of us have emerged from that. Okay. I'm just thinking how stressed I am to cram in the rest of the material into this last 20 minutes, but I actually think I'm okay. I'm doing slightly better than last time, which is okay. We said that materials, they're electrical. They're made out of electrical building blocks. They're made out of an electrical dimension. Let me talk about two categories of materials that are going to be important to us. And their names obviously, they're conductors and insulators. But I just want to say a few words about conductors and insulators. So the fact that materials that are made out of electrical building blocks come in two categories, two classes, two types, was first figured out by Stephen Gray. And Stephen Gray, this is at the time when, huge scientific contribution. So this is huge scientific contribution. It led to the technology of our modern world that there are two types of materials, insulators and conductors. This huge scientific contribution was made by pensioner Stephen Gray in his bedroom with bits of string and tape and wires. He found out from his bedroom in his retirement that there are two classes of materials, so insulators and conductors. What are conductors? Conductors are materials in which those electrons, the kind of light, negatively charged building blocks of nature, can freely flow, freely move through the material. So that's what a conductor is. Examples are metals. Those are the ones we always think of. Copper is a good conductor. Aluminium's a pretty good conductor. Other examples are salt water. So water with salt in it, that's a pretty good conductor too. So those are all conductors. One thing about conductors is if you rub them, so if you rubbed a piece of metal, right, rubbed a piece of copper, rubbed a piece of aluminium, we can't rub salt water, but if you rub that metal and you charge it up, that charge spreads out throughout the metal, across the metal, because it's free to flow. So that's an important feature, distinction of conductors that we're going to meet. What about insulators? In insulators, their characteristic is that charge can't freely move, can't freely flow through the insulating material. Examples of insulators are the materials I've been talking about up to now, with the glass rod and the glass rod and the plastic and the fur and the silk. They're all insulated materials. What distinguishes those, when you rub those, that charge, when we rub the glass rod, it stayed on the glass rod. stayed on the end of the glass rod that we rubbed. When we rubbed the plastic rod, it stayed on the rod, exactly located where we had rubbed it. And so that's a distinction about insulators. Let me say a few words about insulators and conductors in our modern lives and in our actual lives. I was told once that I'm a big bag of salt water. And actually, we're all big bags of salt water in terms of our cells. There's salt water inside the cell. There's a membrane. There's salt water outside the cell. This is a classic example of insulators and conductors. So the intra and extracellular fluids are conductors. There's salt waters, and the membrane is an insulator. So the cell and its insides and outsides, absolutely classic example of insulators and conductors. And understanding the operation of cells, there's a lot of electrical understanding to the operation of cells because of that. Another example, modern day life rather than actual life, is that throughout this building, throughout any building, there's electrical wires. Those electrical wires have a inner copper wire surrounded by a plastic sheath. So that's another example where we're combining now in technology conductors with insulators to transport, to carry charge, to carry what we'll call electrical current from one place to another. So this world of insulators and conductors is important in understanding our own lives, our actual lives in biology, but it's also important understanding technology, how we use technology, electrical technology in our modern lives. Okay. I want to show you these instruments. On the left here, this is the Van de Graaff generator, which is a way of liberating or harvesting electrical charge. That's the way I think of it. And over here is it's called a gold leaf electroscope. It's a way of measuring, quantifying electrical charge. Our electroscope doesn't have a gold leaf. We couldn't afford it, but we have an electroscope. So this is the Van de Graaff generator. Before I touch it, and this here is the electroscope. So we talked about rubbing glass with cat's fur, rubbing plastic rods with silk. It's kind of laborious, it gets old. I want to harvest more charge. Well, the electroscope, the Van de Graaff generator does that. If I switch it on, you can hear if you're at the back probably, and maybe you can see if you're at the front, there's actually a belt. There's a belt that's going around and around in a vertical direction that's rubbing on the inside of the metal sphere at the top. And this thing is charging up. So there's electrical charge being built up on that sphere. I can demonstrate it. If I turn the lights out, you might be able to see it. I'll have to demonstrate it on the left and the right. So I don't know if you can see. I hope you can see that spark. And if I put it over on this side, that's a demonstration of the charge that's being built up. The lights automatically came back on, and half of them I broke. So this thing is building up charge. What I'm going to do is, I'll show you this in a moment, but I'm going to build up some charge on the Van de Graaff generator, and then I'm going to carry it over to the electroscope here, and I'm going to measure some charge. I'm going to detect that charge. The way that the electroscope, I'm going to turn this off in case it gets too much charge. the way the electroscope measures charge is, this is a conductor up here. I'm going to deposit some charge on the conductor. That charge is going to spread out that charge is going to spread out across this vertical arm of the electroscope. So below this metal disc is a metal arm, and the charge will spread out. Because this is a conductor, right? Charge will spread out, freely flow on the conductor. The arm has a solid piece that's just vertical, and then you can see it here, that it's got this movable piece. And if charge spreads out on these two conducting objects, the movable piece will be repelled from the fixed piece. And so by measuring the displacement of the movable piece, we can measure the charge. So it's a way of measuring charge. This is a way of harvesting charge. So let's do this. Let's try, at least try this. Let's try and harvest some charge, and then place this charge on the electroscope and measure that charge. And so how am I going to carry it across? I'm going to carry it across with this. This is another conductor. I'm going to it's like dipping a bucket in a pool of water, but I'm dipping it in the pool of electrons here. I'm going to collect some. And then I'm going to move it over here and deposit on the electroscope. And now you see the movable arm of the electroscope is deflected away from the vertical arm because of the electrical repulsion of the electrons that are excess of electrons that are now on the movable arm and the fixed arm. So this is the electroscope. We're measuring the charge. This is the Van de Graaff generator. We were harvesting the charge. This is called charging by conduction. I basically took a conductor, picked up some charge, and put it on the measuring device. Let me show you it one more time. And now watch closely as I bring up the bucket of charge, which is this sphere here, to the measuring device. So I'm collecting the charge again. Give it a moment. It's filling up. And now I'm going to carry it over here. I'm going to bring it up to the... Oh, that's kind of interesting. Look, I haven't even touched the conducting disk. I haven't deposited any charge on the conducting disk. But still, the movable arm is deflecting from the fixed arm, which means that there must be some electrical repulsion that's going on there. What's the reason for that? The reason for that is that, I can turn this off, that when I bring the sphere nearby the disk, electrons in that disk will run away from the electrons in the sphere. They'll run away, they'll run down the solid arm, they jump onto the deflected arm, and we'll get the repulsion. And this is called charging by induction. So we've seen two types of charging here. Charging by conduction, where I touch the object, and then charging by induction, where I didn't even touch the object, but I just came close to the object. Okay. These two slides I've got in the notes are just a record. They're a record that I demonstrated this, right, to the administration. I wanted to prove that I demonstrated it, and so this is a graphic showing the charging by contact that we discussed when I transferred charge from the Van de Graaff to the electroscope by actually touching it. And this is the second one, is charging by induction. This is where I charge up the electroscope, but not by touching it, but by getting close to it. That's charging by induction. Okay. Let's do We've got 5 minutes left. What shall I do in 5 minutes? You know what I haven't done in today's class? I haven't written down an equation. So let's do a little calculation based on this class. In the upcoming classes, there's going to be more equations. So we will have to get used to that. But I'm going to just do a little calculation. And the calculation I'm going to do is I'm going to imagine a little grain of salt, right? Tiny grain of salt. This can be 1 millimeter by 1 millimeter by 1 millimeter. So 1 cubic millimeter grain of salt. How much charge is in that grain of salt? So we're gonna figure that out. I think I'm going to do this on the device I can't remember the name of, the document camera. We're going to figure out, when I say how much charge is in the grain of salt, we're going to figure out how much charge is owned by all the electrons in the grain of salt. So that's what I'm going to do here. The amount of charge that's owned by the electrons in the grain of salt, that's negative charge. The amount of charge that's owned by the protons in the grain of salt is an equal amount, but is positive charge. Okay, so I started with my picture of the grain of salt. 1 millimeter by 1 millimeter by 1 millimeter. So that's 1 cubic millimeter, or it's like 0.1 centimeter times 0.1 centimeter times 0.1 centimeter. So that's 10 to the minus 3 centimeters. So first thing I calculated was the volume, 10 to the minus 3 centimeter cube. That's the volume of the grain of salt. My route to finding the charge of the grain of salt is, my next step was actually to calculate the mass of the grain of salt. And calculating the mass of the grain of salt, I'm going to use the density of the grain of salt, which I just looked up on Google. That's all I did. Density is mass over volume, right? If I know the volume and I know the density, I can find the mass. So the mass is going to be, I can never do this when I stand up here, rho times V, density times volume. I've already calculated it, but I've already lost the calculation of it. And it is 2.2 times 10 to the minus 3 grams. I mean, pretty obvious, really, because I'm multiplying 10 to the minus 3 by 2.2. So 2.2 times 10 to the minus 3 grams. Next step I wanted to do was to calculate in that mass of sodium chloride, how many electrons are there? The number of electrons. So that step I did in a kind of a bunch of stages. I did them all in one go. I'm going to calculate the number of electrons. If I divide that mass, I made it a lowercase m, by the molar mass, that's an uppercase M. I also looked up that. That was 5.8 grams per mole. Little m over m will become the number of moles that I've got. So that's the number of moles of sodium chloride, the ratio of the mass of my salt crystal to my molar mass. If I multiply that by Avogadro's number, that will give me the number of kind of molecules of sodium chloride or ions of sodium chloride that I have. So that's the number of ions. Each sodium chloride molecule, how many electrons does that have? Well, sodium has 11, chlorine has 17. So if I multiply by the number of electrons in sodium, you won't be able to read this, but it says Z subscript Na for sodium and Z subscript Cl